So now we're going to go ahead and talk about the parallel axis theorem. So we're going to use the parallel axis theorem to calculate the moment of inertia of an object if the rotation axis is not about its center of mass. So let's say, for example, we have a rod. And let's say this rod is rotated about its center of mass, which would be the center of this rod if it's a uniform rod. And again, let's say this rod has a mass m and length L. So we know, looking at our good old truth table, we know the moment of inertia of a rod rotated about its center of mass is going to be 1/12 ml squared. So now let's say we take that exact same rod and we change the rotation axis to here. So I'll call this the new rotation. And again, it's original / center of mass rotation axis. Great, is right there. So for this, am I going to increase or decrease the moment of inertia by moving the rotation axis farther from its center of mass? So go ahead and try it with your pencil. Rotate your pencil about the center. Now rotate it somewhere between the center and the end. Is it easier or harder to rotate? It's probably harder to rotate now. So you're increasing the moment of inertia of that object. So for this, to find the new moment of inertia about the new rotation axis, it's going to be the moment of inertia about the center of mass. And we decided we're increasing the moment of inertia. So we're going to have to add plus m, it's going to be the mass of the object, times d squared. And d, I want to define, is the distance from center of mass to new rotation axis. And this right here is going to be our parallel axis theorem. So let's go ahead and do one practice problem together. We're going to do the problem below. So find the moment of inertia of a thin rod of length L and mass m, rotated about a point at distance of L over 6 from its end. So always, I'm going to go ahead and draw a little picture. So the rod has a length L, and let's assume this is a rod of uniform mass. I should have been clear about that. And mass is m. So the rotation point is L over 6 from its end. Great. So its original rotation axis or point is we have to compare it to the center of mass, which would be right here. So moment of inertia, I about center of mass. So let's go ahead and label a couple distances. So I know this distance right here would just be L over 2. I'm going to go ahead and need in my problem, I'm going to need the distance from the moment of inertia from the center of mass to my new rotation axis. So this distance right here is going to be, so I know the whole thing is L over 2. This is L over 6. So this is going to be, distance D is going to be L over 2 minus L over 6, which is just what? L over 3. Cool. So now we can use this in a problem. So we know our equation is I know, so the moment inertia we want to find about this point right here is the moment inertia about the center of mass plus md squared. So the moment of inertia of this rod about its center is going to be 1/12 ml squared plus, let's see, md we said was L over 3 squared. And again, it's not L over 6, it's L over 3 because it's the distance from your new rotation axis to your center of mass. So let's do some math. So it's 1/12 ml squared plus, this will be L squared over 9, and I like to put the fractions out front, it's just easier for me. So 1/9 ml squared. Great, we can find a common denominator, that's going to be fun. So it looks like 36 is a nice one. So this is going to be 3 over 36 ml squared plus 1/9 will be what? 4 over 36 ml squared. So we're left with 7 over 36 ml squared. Beautiful. And we know that 7 over 36 ml squared is greater than 1/12 ml squared. So we're increasing the moment of inertia if it's rotated a distance farther from its center.